Hello, and welcome again from Chicago. This is High Rise Plumbing Design online with the UCLA Extension University. I'm David DeBoard, and this is week 3. We're going to explore domestic cold water systems. Some of the components involved in cold water systems include the water piping, the flow diagrams, the booster pumps, PRVs, pressure zones, water tanks, and pressure tanks. We will not go into detail on all of these subjects in this session. We will look at more of these later, and especially, for instance, water booster pump systems, we will look at in more detail in week 4. We will also look at water tanks and some various ways of setting up some systems. This time we'll look a little bit at PRVs. Please don't forget to look at the additional reading materials and also the book chapters that I've highlighted in the folders online. And please make sure you do that because we can't cover everything here. As with all of our sessions, we're not trying to learn everything there is to know about water booster pumps and water supply systems. We're trying to see a little bit about how high-rise buildings may require some additional considerations from low-rise buildings. While we're doing that, we will review some aspects that we already know, but we can't look at everything. We can't assume that we're starting from scratch. We assume that you know some of these things already. But we also will provide you with plenty of resources to go online and within the book to find more information. In short, fixtures require a minimum quantity of water at a minimum pressure for them to operate as desired. We design our piping systems, which may require pumps and or tanks to serve these requirements. If it's a high-rise building, it's certainly going to require a pump. It may or may not require tanks. Gravity and friction can interfere with that quest, so we have to build them into our considerations. We have to compensate with an appropriate response. It won't be the same for every. Always keep your calculations in your file and in the project calculations directory. I use Excel to make spreadsheets for all of my calculations. You might use other things. Keep the fixture unit numbers in the drawing file on a no plot layer that can be turned off. There are various ways you could do that. It's nice to have a block with some attributes that have fixture units and GPM, and the size could also be in that block that you don't see, but you can always turn it back on. It could be uh, uh, a live calculating attributes or that are tied to some key, or it could just be a block that's in there so that you can look at it later. Purpose of this is when you redesign something, and there are always going to be changes in a big project, even the small projects, but especially the bigger the project, the more it's going to change while you're working on it. You don't want to have to redesign everything. It's good to keep this information in the files, but where it doesn't plot, so you can access it later. You can also see how you came up with a certain size or other criteria to uh, to check your work or to validate your results. To size a system, we need a few things at a minimum. We need the maximum anticipated flow rate of the system. Of course, we can't design all the piping systems for every fixture running simultaneously and every bit of equipment running simultaneously. The pipes would be huge. There's no way that's ever going to happen in a conventional building, and it's just not appropriate. We also need the maximum and minimum water pressure in the main. We need the residual pressure required at the governing fixture, which could be the highest and furthest fixture requiring the most pressure. So it might not be the same fixture every time. The static pressure loss to get to the governing fixture appliance. And the average pressure drop to the water meter and or backflow preventer required for the system, which they probably are. We look at PSI, which is pressure pounds per square inch, versus feet of head. Head and feet equals PSI times the specific gravity of the fluid times 2.31. Specific gravity of water is 1, so we can take that part out. But PSI is times the specific gravity equals the head and feet times 0.433. So why is that? So here you see a footprint and 1 cubic foot of water. I took that one off the internet somewhere, but this one I made in AutoCAD. It's because this is how I like to explain it. If you have 1 cubic foot of water and it weighs 62.42 pounds, now that varies with temperature, but that's what we consider the typical weight of water. The typical density is 62.42 pounds per cubic foot for our purposes at atmospheric temperatures and pressures. Assuming our cubic foot was 12 inches by 12 inches by 12 inches, the base of the cube would be 144 square inches. If we took 1 square inch from the base and had 1 foot high, that would give us the section that you see in the right hand corner, and that's if we divide 62.42 pounds divided by 144 square inches, that gives us 0.433 pounds per square inch, or psi. So if you have a column of water 1 foot high and it covers 1 square inch area, this will weigh 0.433 pounds. That's where it comes from. I like to explain that to people so that they understand it's not an arbitrary number. This is where it came from. And I'll probably repeat that in the pumping section too. And head and feet equals PSI times 2.31, and PSI equals head and feet times 0.433. Sometimes we talk about head in feet, and sometimes we talk about pressure in PSI. Now, in metric, we have other units that we use, but we're going to focus mainly on the imperial units, but occasionally we'll talk about metric. We also need to determine other losses between the meter and the governing fixture or appliance or equipment. The pressure available for friction, the size of the line from the meter to the governing fixture, the size of the branch lines, the coefficient of friction in the piping material, velocity of the fluid within the piping. As the velocity increases, erosion increases to the power of 5, and as that happens, we get a bigger pressure drop. So it's important to keep your pipe sizes correct and conservative and keep your velocities. When we talk about velocities, I size for 5 feet per second for cold water, 4 feet per second for hot water, and 3 feet per second or less for hot water recirculating, because that's moving all the time. Hot water is more abrasive, has more dissolved air, presumably, and if it's recirculating, it's running all the time. So we want to take care not to erode the piping. Several factors reduce the available pressure. Friction from the interior surface of the pipe, and of course, any joints that are made that are not made properly can have a great effect. Turbulence from every encountered fitting, which again increases if the joints aren't made correctly, and static head from gravity. I'd like to draw a system riser flow diagram. We need to create this simple map of a system so that we can form the basis of our design. We need to identify the path of the water and account for the factors that affect the design. Should include anything that would have an effect on the flow and or pressure of the water that we want to deliver. Our flow diagram must include the complete water distribution system, but that doesn't mean that we need to have every detail. At this level, we just want to have the main path and the main factors. At this point, we're not even going to know all the details. This is something we do early in the we can enhance it as the design progresses. But this diagram should include the incoming water pressure, the elevation of the incoming water service, where that pressure was taken, the floor-to-floor heights, the static pressure at each floor, the minimum pressure required at the most remote fixture or piece of equipment, the water meter, and the main service backflow prevention devices if required. In Chicago, we have them only on the fire. We don't have them on the water. It's up to us to design them at the individual point of use where required in Chicago. From this flow diagram, we can determine a few things. We can see the pressure needed at the end of the system, the pressure required to overcome the static from gravity, and the PSI that's available at any point. During this upfront, doing this upfront in the design process again gives us and the other team members also a good estimate of the services that we will require to build our project. This helps us to get information for the pump power requirement. Here's a simple main flow diagram. You may have seen this in an article in a magazine a couple of years ago that I did for PSD magazine. It's very simple. It just shows on the left we are looking for elevation, PSI, the fixture units, GPM, and the size. We should have that on the incoming water service. Comes in, you have a water meter, booster pumps, and then you have, again, you put additional information as we did at where the water was coming in. Now after the pump we put it in, and we also want to know the horizontal distance to the most remote fixture. And we look at the elevation plus the horizontal distance to give us the total distance, because you're fighting friction whether it's horizontal or vertical. We also need the elevation to the most remote fixture, and we need to know what kind of pressure, what the elevation is, etc. at that point. We can include this in our drawings also, even if we are using Revit or AutoCAD MEP 3D or some other programs. We can still include a diagram like this, especially in the scope documents, because it shows the main system requirements. We could use these other programs to generate 3D details of the system, and that has other advantages, but this main system flow diagram can be used before the drawings are complete. It can be used even at the very early stages of development, and it helps in the design process. And it will probably need to be updated as the project progresses if we're going to keep it. I like to keep it on the drawings, but I made it myself, so I'm partial. This is one of my later versions, and again, this is in Excel. I used a white highlight on all of the cells that are not a different color. Uh, that wipes out all the graph lines, the grid lines. This provides a complete overview of the system, which is vital to engineering a complete system, of course. So even when we do generate 3D details in Revit or other programs, we can use this diagram A lot like we would use a key plan to see how the pieces fit together into the system. That's why I like it. Now, if we take a look here, we see in this case, I have the blue boxes that we fill in. The yellow boxes are filled in by Excel as it calculates and picks up information from the other boxes. So you can see that here, by doing it this way, we can also calculate the pressures for the pump and the horsepowers and GPMs. So you can see down on the bottom section, I have a box, an orange box that says electrical requirements. You can give this to the electrical engineer right away, so at least they have an idea. Now, sometimes the height of the building changes and other things change, so this could change, but it at least gets them in the ballpark. They know what kind of power they're looking for. Notice by BP1, it says 3 in one of the blue boxes. So in this case, I put a 3 in there, so that means I want 3 pumps. And when I did that, it split up the horsepower. You can see that the BHP I need is 62 according to my calculations down below. Now, these pumps are never really going to need that. So if I have 3 at 60, I know that that's enough. The third pump rarely, if ever, will even run. But we need to make sure that we have the pressure to get up there. So we designed the the pumps to have the GPM split between the number of pumps, but the pressure to be the same for all the pumps so that one pump could provide enough pressure to get to the top at the reduced flow. I have actually my first article, magazine article, was about VFDs and how most of the time we hardly need any pumping energy at all, but that's another subject. So to determine our pressure requirements, we use the plans and diagrams, and we determine the longest run to the highest fixture in the system. We multiply this distance by 0.03 to calculate the pressure required to overcome friction based on that distance. This is based on a 3 psi loss per 100 feet. And this is a starting point. You don't have to use 3 pounds per square inch per 100 feet, but that's an acceptable number. Normally 2 to 5 are the numbers that we would design to, but this gives us an allowance of acceptable pressure drop of 3 psi per 100 feet of linear pipe run. This is a typical number, arbitrary, somewhat, yes, but it's a good number to use. For instance, you wouldn't want to say a 10 psi loss per 100 feet because now you're going to make the pumps bigger than they need to be. And you wouldn't want to make it too small with the 1 psi loss per 100 feet because now you might find yourself short. And there are all kinds of variables, so 3 is a good number from experience. To determine our pressure requirements, we're going to multiply this number by 150% to allow for fittings and valves. Remember, this pressure is just to overcome friction at this point. And this would be the pressure required to overcome friction to the governing fixture that we spoke about, the most remote. We'll add this PSI to the minimum PSI required at that fixture. Now, add the pressure required to overcome the other losses, such as the meter and a backflow preventer. In there yet. Once we put the static in, we'll have everything. But right now, this is the pressure that we need, excluding the PSI needed to overcome gravity for the vertical riser to serve the fixture. By adding this to the total static, which is, again, to fight gravity, we will determine the total pressure requirement of the system. This is the PSI that we need to consider in determining our system pressure requirements. Again, PSI versus feet of head. Make sure you're talking about pressure or feet. Step by step. First, we find the static pressure by multiplying the height from the main. This is also the head, but if we're looking at it in feet, it would be head. In pressure, it would be the static pressure. And if we know how high it is to the highest fixture outlet, we multiply times 0.433 to get the PSI. Measure the distance to the remote fixture. Then we get the discharge pressure of the pumping system minus the head and PSI to get the fixture, to get to the fixture, minus the PSI needed at the fixture. The number left is what we have available for friction. Divide this distance in feet plus 50% to 100% for fittings and valves. So 50% is a good number to add for that. Again, you can add up every fitting and every valve. The more complex the building, the more difficult that will be, especially given that the design will be changing all of the time. So 50% is a pretty good cushion and it will give you pretty good results, and you'll see that it won't affect the results really that much. It's not really oversizing anything. And you get the PSI available per foot. Chart reads in PSI per 100 feet, so multiply by 100. What about flow? So to determine our flow requirements, remember the pressure requirements are based on the most remote fixture, and that is at the highest PSI, or the fixture with the highest PSI requirement, usually at the highest part of the building and the furthest away from the pump. But the flow requirement is based on anticipated flow of the entire system. Remember that not necessarily all of the fixtures and equipment in the system are running simultaneously. It's never going to happen, but still considering the entire system and allowing for reasonable factors for probable simultaneous flow. That is what Hunter's curve is about. Plumbing engineering, I sometimes call it voodoo engineering, but it's basically full of statistics. And while some people would say, well, that's rules of thumb and etc., no, it's even higher mathematics than you would normally use, because you have to take consideration for the probability of the number of people who would do something at the same time. With plumbing, that is the great unknown variable is the user. You never know what people are going to do. With HVAC engineering, it sometimes appears that it's more concrete engineering, but it still has variables based on weather conditions. And the weather can change every year. It might not be the same in that particular location ever again. And so they have the variables of weather, we have the variables of people. We try to predict it based on what they do statistically, just like for HVAC, you would use weather charts, what was done historically, but that doesn't mean it's going to happen next time. But it's close enough. So to determine our flow requirements, we need to assess all of the risers and branches of the entire system. This flow diagram does not have to show all the fixtures, but it does need to include the quantities and water supply fixture units for each branch as it connects to the system. This is required to size the water supply service main and the domestic water booster pump system. Another factor is pressure. Well, it's all about pressure, really. The maximum pressure allowed to be supplied to a plumbing fixture is generally 80 psi by most codes. Some codes are more than that, but usually 80 psi is the maximum, and for good reason. The fixtures could probably were probably designed for something more in the neighborhood of 120 psi maximum, but 80 psi is our maximum pressure allowed to a plumbing fixture. In a high-rise building, it is likely that we'll need more than 80 psi to provide psi needed by the fixtures at the top of the building. We need to determine how much we need at the top and how much it will take to get there, and to determine the psi we need at the pump. When this exceeds 80 psi, we will need more than one water supply zone. At least one of these zones will require a pressure reducing valve, PRV, to reduce the pressure so that no more than 80 psi will reach any fixture. Here's an example of a zone chart. This shows cold water upfeed, hot water downfeed. This is not a preferred method. Try to keep the hot and cold water zones together if possible. This helps balance the pressures and can alleviate some problems that we've seen in the field, where theoretically the pressures are going to balance, but anomalies can develop. So on the left, we see the upfeed system. We have cold water feeding up. We have a PRV for the first zone, and then we go up, and we have a PRV for the next zone, and then we go up to the top. We don't need PRVs because we designed the pressure to not exceed 80 psi by the time you get to that 20th floor level. On the right, we see a downfeed system. So in this case, we have water heaters not indicated here up on the top, which is relatively common. You almost always want to have the water heaters at the top. Sometimes you can't. We'll talk about that later. And then you see a downfeed system. And here we separated it into uh, different zones for the cold water feeding up and the hot water feeding down. Here's a bigger building and a little more detail. It indicates the pressures from different perspectives, showing how much pressure it takes to get it to the top and how we can break the risers down into zones, controlled by PRVs to avoid sending too much pressure to the fixture. So here you can see with the high zone that a PRV is not required. And then we see, well, in this case, we have four zones. So we have, and I named, in this case, high zone 2, high zone 1, low zone 2, and low zone 1. We could just name them 1, 2, 3, 4, or, different things. A lot of times you have three zones, a low, a mid, and a high. Since I had four, I chose to do it this way. So this is also from Excel, also easily uh, captured and placed into your drawings. We see on the left, we see the floor, and then we see the elevation in feet and inches, and then we see the height in decimals, and the floor to floor height, which is derived from those numbers. See, a lot of them are 11.5, but some of them are different. And then we have some that are 12 feet, we have some that are more, we have some that are less. And this is an older building that's being totally uh, redesigned and repurposed, going from an old office building to a new residential hotel. So you'll notice that the 21st floor has 17 feet. That there's also a mechanical interstitial space there. So then we see the total PSI, what it would take if you had 29.80 at the bottom that you would have, and you only had one zone, it would take 231.65 psi at the top. And we have the static based on our conditions where we have 0 at the basement 2 level, and then PSI for each zone, or PSI if you were feeding down, and then we have the zones, how we broke them up in the zones. So these could be, you could do this with similar results, up feeding the zones or down feeding the zones, or you can take one floor and up feed to one zone and down feed to the other with 2 sets of PRVs in the same closet, PRV closet. Don't forget that PRVs have relief valves and must have a floor drain. Otherwise, you'll have problems. If they fail open, and they have to have a relief valve to dump the water. This would be a great time to view the posted material about PRVs. But before you do that, let's take another look at the previous slide. You can see a lot of information here. I've covered a lot of it. You can see that you can have, depending on how you do your system, you can link the cells on the right for the PRV. You can link them to give you the PRV pressures in and the pressures out. So it's very easy to do that. It's very easy to change. I use different colors to help me keep track of it visually. When you put it on the drawing, you probably want to change those all to white, or you might use some light shades of gray so that you can read them on the drawing if you don't. So this is one example of how we might chart our zones and determine our PRV requirements. I like this method, not because I developed it, well, that's a good thing too, but because I can view different bits of data and I can modify the zones without starting from scratch every time. I don't like to do anything by hand on paper. I like to do it on computer-based media of some kind, and then I can keep that in a file, because frankly, am I going to remember everything that I ever did? And if something comes up later, I would like to have something to go back to see how I arrived at the conclusions that I did and who made me change what so that it didn't work. Because if it's not working, I'm assuming that's because someone demanded that we make some changes against our will. I'm assuming. So it's common for the building designs to change many times, especially the more complex the building, the more it's going to change. And you're going to have to redesign things. If you have it in a digital format, it's easy to change some of those parameters. Week 4 materials are closely related to these systems because that's when we'll be looking at booster pump systems. We'll look at other related subjects like water storage tanks, water hammer, and other topics in future. Now, review the chapters from the book that I highlighted and the other materials that I posted. A quiz will be posted. Please get that in within a week. If you have questions, answers, complaints, comments, etc., use the forums, and hopefully we can all share. I've noticed some people aren't doing that. We need to get everybody online. We can learn more by sharing our own perspectives. Homework, well, that's the quiz. But that and other assignments will be listed on Blackboard. Please review the homework policy. Let me know if you have any questions or comments regarding this. Technical questions or problems, please go to help support. Technical support is better at that than I am. I will try to answer your questions and answers. And thank you for viewing. Don't forget that homework. Don't forget to look at the other resources. Thank you.